So what we are trying to calculate is, we try to calculate delta V1 and delta V2. Okay. For that we need to, this is where we start. Do we know this A? Huh?
A is the same as the target orbit.
What is A?
First, it
Huh?
is equal to the initial orbit, and then at the other side it is equal to the target orbit.
Isn't A like RA plus RP divided by 2?
So what is it? R1 plus Rp divided by 2?
Yeah.
So you know that as well, right? A is only 1 for any given orbit. We are only interested in the Bowman transfer orbit. See, this is what we want. Okay, keep in mind. We assume, see, because when you say target orbit, you should know the target orbit, right? We should technically know where we want to go. It's not like we're just going into one orbit just for the sake of doing a Bowman transfer. We know which orbit we want to go into. We also know which orbit the satellite or the launch vehicle will take us. This is where the launch vehicle will take us, the initial orbit. So as spacecraft engineers, you may not be so involved in how you get to the initial orbit. Who will be more involved in this part of the design problem? Huh? The propulsion engineers. Mostly the propulsion engineers and rocket engineers. Okay. Of course, you can do that as well. But as you here focusing on this course, you are more interested in taking your satellite from this point to this initial orbit to target orbit, and that's what we are focusing on. So you have this can simply be written as h square over 2 square over mu RA plus RP divided by 2. Okay. I've just substituted for this E here and got this. Okay. And this RA plus RP is simply 2R. If you substitute E here, you'll end up with this. So this means H is equal to root 2 mu root of RA/RP divided by RA plus. Now, if we know H, can you, here H is known, right? Everything is known on the right hand side. Can you calculate the velocity now? From this, can we compute velocities? It's a simple relationship. What is this relationship between velocity and angular momentum, and V cross R, but this is magnitude.
It was R equals, I mean, H equals H and R.
At this point, so remember, recall this.
Oh. Is it a V times
VP
R, V
times
times
RA.
R?
VP times RP or RA times VA. Got it?
Oh.
Louis, that's what you're trying to say?
Right.
So what were you trying to say?
I was going to say cosine, the one that has cosine, you say that's an active, right?
Right.
But I was wondering, that wouldn't be it.
So cosine, if you do the cosine, the angle between, if you have to do sine, you cannot do cosine because this is a cross product.
Right.
So you do a sine, the angle between V and R is how much? At any point, the angle between V and R is always 90 degrees. So sine of 90 is 1. So you just end up with E times R. Okay. So if you from this you can say, see H here is the same as H here, right? You agree? For the elliptical orbit, for the transfer orbit, H here is the same as H here. Can you calculate the velocity V1? What is V1? Sorry, not what is VP? So here I'm also going to say we know R1 and V1. Okay? Can I say that? Is this okay? Is this statement okay? Again, go back to your homework. What you did was, the first part was you were given R1 and V1 and you were asked to compute the orbital elements, which you did from MATLAB. You also did the reverse. You were given orbital elements. You were then required to find R1 and V1, R and V. You don't remember? You haven't done your assignment? Everyone? You don't remember doing this?
That was my problem, 15 or 20.
You don't remember doing this? So if you know these, you can calculate these. If you know these, you can calculate these. Okay? You can interchange that. So what is VP? VP is simply, so here you can say H is equal to VP RP VP, that is equal to RA VA. Okay? So your VP would be what? H divided by RP, which is H divided by R1. And similarly, VA is equal to H divided by R2. If we know this, did we calculate, now can we calculate delta V1? Delta V1 is VP minus V1. Delta V2 is V2 minus. This is small x. Now tell me something. Your R1 and RP are the same, right? Most of you agree with that. Is V1 and VP the same?
The magnitude is different, right?
Now tell me at this point,
The direction is the same.
huh?
The direction is the same. Right?
Direction is the same, but the magnitude is different. At this point, will the initial orbit and the transfer orbit have the same angular momentum?
I don't think so, because one is circular, one is elliptical.
Yes.
Huh?
Which one?
Yes.
At that one?
At periaxis?
Uh-huh.
At
Oh,
that
yeah,
one?
that saying
I'm asking about angular momentum. Will h of the elliptical orbit and circular orbit be the same at this point?
Yes.
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 Think about it.
let's see.
Louis,
Yes, sir.
question? Ms. Noble?
Okay, R
My question is, at this point, will the age of the circular orbit, the initial circular orbit, and the elliptical orbit or the transfer orbit be the same?
I don't see how any is going to be different. I don't think so.
The age, I'm talking about age.
But R is
Huh?
gonna be the same. R is
R
gonna be the same, so it's be at that point.
It depends on RA, RP, and V1. Both are
All
the
the R and B are part of B, so B is big.
Yeah, I think they'll be the same, because they're the same distance from the focus point.
That's what this is a trick question for you. Don't do this, okay? The angular momentum of any orbit at any point is the same. The angular momentum of this orbit, regardless of whether it's here or here, it's the same. I cannot, first of all, the first trick question was, I cannot ask you if at this point the angular momentum is the same. You should say you are not making sense. Okay?
I said, I don't see how the B is.
Okay. So yeah, that's what. And the thing is, what h cannot be the same. H is a function of A. Okay. A semi-major axis. Is the semi-major axis? H is a function of A, right? Is the semi-major axis the same for circular orbit and the? It's not the same. It's bigger, right? The semi-major axis for the elliptical orbit is much bigger than the semi-major axis for the circular orbit. So h is not the same. So what is this h?
What do you mean what is this?
Are you saying
Which h? Yeah, which h is this?
for the transfer or
This is the transfer orbit h. Okay. So this h is not the circular orbit h. Keep in mind. We are only interested, again, we are only interested in calculating the transfer orbit. The V1, this is our goal. As spacecraft engineers, this is what we want. We are interested in knowing what this delta V1 is. Delta V1 is the change in velocity. How much more velocity should you induce to go from this orbit to the initial orbit to the final orbit? Okay. Now you want to take a look at an example. We'll take a quick look at an example. So you have a 2000 kg spacecraft. And it's in a 480 by 800 kilometer orbit. So the first one is find delta V. Alright, let me make it interesting. It's not in a 400 by 800 kilometer orbit. It needs to go from a 480 to 800 kilometer circular orbit. Okay? So find the total delta V. The question is find total delta V. This is a very simple problem. So what is total delta V? First of all,
V2
huh? V1 plus V. No,
delta
delta V1 plus delta V. So because we are not, see why, does it matter which direction we are talking about? We are only talking about magnitude, right? We are not doing the vector thing. So we just add the two delta V's. You're right. So what is delta V1? How do we calculate delta V1?
VP minus
So solution, so you have delta V1 is
VP minus
Vp minus V1. Okay? Do you need more information here? What do we know? And delta V2 is V2 minus Vn. What is R1? R1 equal to Rp is 480 plus
the radius
6378. Six eight 58 kilometers, and R2 equal to Rp is what? 300 plus 717.
Isn't it R2 equal to RA? I meant RB.
So what is H? We know everything over here, right? So you have H is root of 2 into root of RP divided by RA plus. This is equal to so now what is V? What do we know? Do we know VP? Huh? So can we calculate V? What can we calculate from this? H over RP is VP. So what you're going to get is 52,876.5 divided by RP is 6858. So what is this? 7.7 kilometers. That's what it is. And what is VA?
H over RA.
How much is this?
We calculate.
6.
What is V1? Can we calculate V1? See, H over R1 is V1, right? So can we assume H is the same at this point and this point? Can we take the same H?
Yeah.
So that's what you were saying before.
Can we take the same H?
H is the same, right?
It's not the same. I just asked you the question a while ago. You cannot take the same H. You stand up for Brandon. You have to boycott the class if I say that, okay? So what is H1? H1 is simply mu r. See, here, think about just this, okay? So H1 would be for the circular orbit. This would be simply r square over 2r. Right? For the circular orbit, can I apply this for the circular orbit? H. H1 would be what? R square. RA, RP is the same. RA plus RP is the same. It's simply R square over 2R, which would be R over root 2. Right? So H1 would be root of 2 mu root of R1 into R1 divided by 2R1.
Why are you not saying R1 squared?
Huh?
Why wouldn't you say R1 squared?
Yeah, R square, it's the same thing. I'm just cancelling this. And I can cancel this with this, and this will end up with root of mu R1. Got it? So now I know H1 because I know R1. This H1 is the angular velocity or angular momentum of the initial circular orbit. No? Not following?
It's circular because you can use the fact that you make R squared makes it circular. If they were different, you wouldn't need to say R squared.
This H is the H for elliptical orbit, right? So this H is the H for H1 is the H1 for initial orbit. Okay. So now you can, if you know H1, right? So this we know how much is this? Can somebody tell me how much is this? So mu. All right. I'll just give you the rundown. You can complete this problem on your own. Okay. Now,
How much is
mu is assuming this is a.
398,600.
It's assuming you are
This is
in a circle in an Earth orbit. Okay, you can just assume the mu values 3980. It's a constant. Okay. Now can we calculate V1? V1 is H1
Over
R1.
right.
Is it H kilometers squared?
Huh?
Over second squared?
Oh, I got
We got H1.
52,283.
52,283.
Yeah, these units not adding up, right?
Yeah.
But starting with H.
Hmm?
For
The
H1.
units
H over RP.
yeah, with H over RP, some of these units is not adding up, like above it. Is that supposed to be kilometers square?
Kilometer per second square.
So how would H over RP be kilometers? If RP is kilometers,
You're right. It's kilometer square per second square.
That's what I think so, because kilometer square is acceleration. Well, it is angular acceleration. So that's angular velocity.
Don't the numbers stay the same?
Hmm?
Don't the numbers stay the same?
Let's focus on the numbers. I'll tell you about the unit. Huh?
I'll verify it.
Yeah. Okay. But the numbers will remain the same. Just focus on the numbers for now. Now, can you calculate V1?
Yeah, take that value that we just got paid.
Yeah, and you know R1. R1 is the same as R2. So what I want you to notice here is, see here if you look at this, this R1, this AH1 has to be smaller than this. Right? Because, see RA plus RA RP, RA is bigger than RP. Right? You see that? Everything is the same except that this mu is the same, but RA becomes RP here. So it reduces, the value reduces.
So in this problem, RP and RA for H1 and there would be 480 and for R2 it would be 800 for both.
800 plus this. 800 plus the radius. We are talking, this is altitude, right?
Okay.
You cannot be in your RA-RP cannot be just 800. What happens if it is 800? If RA is 800 kilometers, where will you be?
In the middle of it.
Huh? If RA is 800 kilometers, where will you be?
Will you not be inside of it?
Huh?
This is being Earth.
You'll be inside the earth.
Yeah.
You got it?
So that's why you have to add the H on it.
Right.
It won't be inside of it.
So you cannot orbit inside the earth, right?
Well, you could, maybe.
You could if you just dig around earth and then you can actually orbit around it.
You serious?
Huh?
If there's enough free space, if you can open up the space, you could take it.
If you have a tunnel, maybe you can do it. And can you calculate H2 the same way? H2 is equal to
Yes.
root of mu R2, and from this you can calculate V2. This is H2 divided by R2. Once you know these two, V2 and V1, so you know delta V1 and delta V2. And once you know delta V1 and delta V2, you add delta V1, delta V2, you get delta V2.
It makes so much more sense when we start working it out. I got it.
So now, is this clear how we do a Hohmann transfer?
Yeah. Can we change the units to kilometers square?
Sure, I'll check that. I'll check that in a minute.
It's just kilometers square per second.
Huh?
It's the square is on the wrong side. That's all. I'll put H.
Kilometer?
Kilometers square per second.
Yeah, that makes sense.
Kilometer square per second.
That's what the book has.
Alright, let's
This
use that.
represent.
Hmm.
You said this H1 is for the circular orbit, right?
Hmm.
This H2 also is for the circular orbit.
The bigger one.
Okay, the big.
We have to go from H1, we have to go from orbit 1 to orbit 2, and this is the intermediate transfer orbit. Initial is H1, the target is H2. Make sense? Everybody, is it making sense?
Yes. And
And the
and to shift the transfer.
Right. This is H, just the transfer. So how you are given only very limited information, right? You are given what is the mass. You did not even use the mass. Right. Delta V1. How does mass come into picture now?
I don't know.
So you have calculated delta V1. Now you think about
You said
the first impulse equation we talked about, the ideal rocket equation. Ideal rocket equation was
the fact that you lose some of your mass as you go higher.
right. So delta M
Over the.
over M is equal to, we have that 1 minus e to the power of minus delta V, I think I S P G1. Right? So delta M, this M
It's going to change.
is that M, 2000 kgs. So that includes the fuel, onboard fuel. Delta M is what? How much fuel you have to expend. And that fuel, this ISP is the property of that fuel. Got it?
Just some fuels are more efficient.
Some fuels are more dense than the other fuels. If you are using a solid rocket booster, this will be really high. Okay, then your mass loss will be, you don't have to lose as much mass. You have to, limited mass loss, you can achieve that delta V. This delta V is, so you use, can you do a maneuver with solid, can you do this maneuver with one solid booster?
No, you need more. Well, no, actually you can because it's denser, so it can take less.
You can add, see, you cannot do it, again, this is slightly outside of what we are discussing. You may not be able to do it with one because what happens is, once you light up your solid boosters, you cannot stop it. So you need at least 2 solid boosters if you are using solid boosters.
2 stages.
2 stages. Not 2 stages, but 2. Yeah, you can say 2 stages. So you burn one, you go from here to this orbit. You burn the other one here and go from here. If you use something like a fluid, you can expend a little bit of that fuel, that delta M in this, and the other one in this. Why do we have to burn it?
What do you mean by you have to burn it?
Why do we, see,
That's the only way to burn it, so if you don't have anything else, you can't.
do you really, in space, do you really burn the fuel? Can you really burn the fuel?
You just create a reaction, right?
Huh? How do you achieve this mass loss?
Start a chemical reaction inside the chamber and let it go out. I don't know.
You can use simply pressure difference.
Um,
You use a pressurized thrusting container. If you release the valve, what is going to happen? The outside pressure is how much? It will be practically 0, right? So there is a potential difference. So it will go from a higher potential, which is inside the can, to a lower potential, which is in the atmosphere, in the space. So that mass loss, entire system is losing mass, right? So that mass loss will create this delta V. You got it? Can you burn fuel like you burn fuel on a rocket?
No.
You cannot really burn fuel because you don't have oxygen.
I thought you created oxygen or something inside of the chamber too. I thought
You can
the
do
reaction
that.
was inside of the ship.
Right. Actually, generally that happens. But generally, it's not really required to burn the fuel. Okay? So if you just release it from high potential to a low potential, you'll achieve that delta V and you can go. And that's how most thrusters work. Your exams will actually do it just before you go for your Thanksgiving break. We'll do it on Tuesday. Huh? So Tuesday you actually are here till 12 noon.
Yeah.
You want an early break, Karen?
No.
You are here till 12 noon on Tuesday. You have classes till 12 noon. So we'll just finish. I think it will give you some extra time as well to study.
Yeah, our homework.
Huh?
Yeah, our homework posted right now, right?
I'll post it today. Extra homework, homework which is focused on coordinate transformation.
That's what we're going to test, correct?
Your test will be whatever you did for homework 5 and this one.
Okay.
So it will not be just that.